Statistical mediation analysis is one tool to gather some clues about whether it is plausible for one variable, the mediator, to partially explain the causal relationship between two other variables. And it basically comes down to fitting three linear regression models. First, a model with the manipulated variable predicting the theorized outcome. In R, you could get this with lm of y tilde x. Simple linear regression. Y is the response variable, x is the predictor. This is like making sure coffee actually increases overall math test performance. Second, a model with the manipulated variable predicting the theorized mediator. In this model, m is the response variable instead of y. This is like making sure coffee actually increases the concentration of caffeine in the bloodstream. Third, you'll fit a regression model with the manipulated variable and the mediator, additively predicting the theorized outcome. This model has two predictors, which you'll get by using the plus sign to separate the two variable names in R. This is the most difficult model to understand, but the basic point is to show that caffeine in the bloodstream is correlated with math test performance within the conditions of the experimental manipulation. We are interested in the slopes from those three regression models, so we often label those slopes with letters for convenience. This is the first regression model with the manipulated variable predicting the theorized outcome. We don't care about the intercept for now, but we will call the slope c. In the second regression model, with the manipulated variable predicting the theorized mediator, we will call the slope a. In the third regression model, with the manipulated variable and the mediator predicting the theorized outcome, we call the slope of the manipulated variable c prime, and the slope of the mediator b. So these are the three regression models, represented in terms of generic variable names x, y, and m, and also represented in terms of the example I'm talking about with coffee, caffeine, and math score. It is fairly common to use these specific variable letters to represent the variables playing these three roles. X is the variable theorized to kick off the process, m is the mediator, and y is the outcome. But now I'll just use the variables from the example because it's less abstract. There is a key equivalence among the slopes from these three regression models, which I've somewhat facetiously nicknamed the fundamental theorem of statistical mediation. It's a times b equals c minus c prime. If these are linear regression models fit by minimizing the sum of squared residuals, the way that we've been talking about it all along in this class, then the actual slope estimates will always satisfy this equation. The slope of coffee predicting caffeine times the slope of caffeine predicting math scores adjusting for coffee will be precisely equal to the slope of coffee predicting math score on its own minus the slope of coffee predicting math score adjusting for caffeine. Isn't that kind of amazing? Here's another way of representing these relationships. An arrow in this kind of diagram represents a regression slope. At the top of the screen is a representation of the model where coffee predicts math scores without adjusting for caffeine, without including caffeine as a predictor. The slope in this model is labeled c. In the middle of the screen is a triangular diagram representing the other two regression models together. Caffeine has only one arrow pointing toward it. So when caffeine is the response variable, the only predictor is coffee, and the arrow labeled A represents the slope with coffee predicting caffeine. Math score is not involved in that association in any way. Math score has two arrows pointing toward it, so this diagram indicates that there is a model in which math score is the response variable and there are two predictors, coffee and caffeine. These are treated as additive predictors or main effects, just two terms in the same regression model. The slope of caffeine in this model, adjusting for coffee, is labeled b, and the slope of coffee, adjusting for caffeine, is labeled c prime. A times b is equal to c minus c prime, and the value a times b, equivalent to c minus c prime, is called the estimate of the indirect effect. Estimating this indirect effect is the central purpose of statistical mediation analysis. And of course, if you add c prime to both sides of the equation, you can see that a times b plus c prime equals c. The slope c is also called the total effect. It represents the total difference between the average math test score in the coffee condition and the average math test score in the no coffee condition. C prime is called the direct effect. It represents the difference between coffee and no coffee adjusting for caffeine. Any benefits of coffee due to its great taste or warmth, improving people's mood, would result in higher test scores regardless of caffeine, and all of that stuff is lumped into the direct effect of coffee. I already said that A times B is the indirect effect. So this equation means that the total effect can be broken down into the indirect effect plus the direct effect. Again, the total effect can be broken down into the indirect effect plus the direct effect. To me, the trickiest part of all of this is thinking about why the B path is so important. It seems clear that a conceptual mediation story would need the A path. If caffeine is a reason coffee causes better math test scores, then coffee has to cause changes in caffeine. That much is obvious. But why the B path? Why should we estimate the association between caffeine and math test scores adjusting for coffee? It might not be obvious at first, but as long as everything has some randomness in it and these cause and effect relationships are not perfect, then the B path is related to the idea that X causes Y because of M. If M is a more immediate cause of Y than X is, then M should probably be associated with Y even if you hold X constant. If caffeine is a more immediate cause of math test performance than coffee is, then caffeine should probably be associated with math test scores even if you hold coffee constant. For example, within the group who drank coffee, the ones with more caffeine in their system should still score higher. Why? Let's think about randomness for a second. If the predictor X causes changes in the mediator M, but this does not happen with perfect precision, then there will be some variability in the mediator M that is due to X, and some variability in the mediator that is not due to X, that is random. In my example, there will be random variability in people's level of caffeine. And if the mediator M causes changes in the outcome Y, but this does not happen with perfect precision, then there will be some variability in the outcome that is due to M and some that is not due to M. Math test scores will have some random variability unrelated to caffeine. If coffee operates through caffeine, at least in part, then some of the variability in math test scores that is due to coffee will be redundant with the variability that is due to caffeine. But caffeine has extra variability that isn't due to coffee, and this extra variability should also influence math test scores if the theory holds. So we should be able to detect a relationship between caffeine and math test scores even when we hold coffee constant. Of course, we don't know that the association between caffeine and math test scores adjusting for coffee represents a causal relationship. Those are both just measured variables, not manipulated. But we still define the indirect effect based on the effect of coffee on caffeine and the association between caffeine and math test scores adjusting for coffee. Both of these slopes are an important part of the logic of statistical mediation, so we need to test the claim that both of them are large enough to count. The product of the A path and the B path is only large if both are large, because that's how multiplication works. For example, if one of them is 0, the indirect effect will also have to be 0, no matter how large the other one is. So the indirect effect is large if coffee has a large effect on caffeine and caffeine has a large association with test scores adjusting for coffee. To repeat something I said earlier, estimating this indirect effect is the central purpose of statistical mediation analysis. If the indirect effect is almost as large as the total effect and in the same direction, then the direct effect will be small because the total effect is equal to the indirect effect plus the direct effect. The difference in test scores between coffee and no coffee is equal to the indirect effect plus what's left of that test score difference after we take out all the variance explained by caffeine. So another way to think of the indirect effect is this. It's how much smaller the direct effect is compared to the total effect, how much smaller the coffee test score differential gets when we take out what portion is explained by caffeine. But this way of thinking about the indirect effect really only makes sense if it is in the same direction as the total effect. There's a big caveat about all of this. This statistical procedure only helps explain a causal relationship between x and y if you know that the relationship between x and y is causal in the first place. Your undergrad stats classes probably drilled into you that correlation does not equal causation, and that stays true even when you're using fancy stats. Running a mediation model on correlational data does not make the data less correlational. Also, this diagram in the middle of the screen has 3 arrows in it, but drawing an arrow doesn't make an association causal either, even when you've manipulated the x variable. The coffee, the B path, the relationship between caffeine and test scores, is just an association with no special causal evidence of its own. Going back to conceptual mediation. This is why one study isn't enough to demonstrate a process. In the long run, as you carry out a program of research, it might be a good idea to manipulate the mediator in other ways to show that the B path can also be causal. But even having manipulated the mediator separately, there are still unsolved problems. If we know that X causes M and Y in one sample for at least some people, and M causes Y in another sample for at least some people, does that mean that X causes M and M causes Y for the same people? No. That's a separate problem and a difficult one to address. Recall from earlier, for more on this topic, see this paper by Bullock and colleagues. Link is in the description.